Hello, good day. How are you? Welcome back to Statics. We are on lecture number 8 now, and we are about to complete our section 9. Mass moments of inertia is backtracking back to the objects. We were discussing, first of all, weights and forces. Then we converted to areas. And our study became completely mathematical. So it was just areas, the geometry, centroids, distributed loads in terms of just the areas, right? And then now we are converting back. So we want to come back to the object, and we want to measure its mass and so forth. So this is now a process of backtracking or reinterpreting the moment of inertia in terms of mass. And this is the most important part, because I'm sure all the conversion techniques, we now have them, all the tables for the areas, we now have them. How can we then convert all these techniques so that we can analyze object of a given mass and actually calculate the moment of inertia in our SI units in terms of mass, or the US customary units? So this discussion will basically focus on just section 9.5. We will focus on just section 9.5 on mass moments of inertia. Remember the term second moment. When we introduced the term second moment, we said the second moment is the correct term for moments of inertia of areas, because moments of inertia in general are related to what or refer to mass moments. So now that we could use it interchangeably for the sake of using our symbol, now we will deal with the real mass moments of inertia. So it means then when you are speaking or discussing with your engineering techniques fellows and colleagues, you need to be specific. When we are discussing moments of inertia, what are we talking about? Are we still discussing the second moment, or you're now talking mass moments? So you can even include this word just for you to be in sync. Right, so for us to look at mass moments, we will look at simple masses, right? Mass moment of inertia of a simple mass, and then we will extend to the parallel axis theorem. The parallel axis theorem, we had already introduced it in terms of the moment of inertia about the x and y axes or other axes, and then we now are looking at, and then we also had it for the product of inertia. So now we are just re-looking at it in terms of the mass moments. And then moments of inertia of thin plates. So the thin plate is the starting point of our mass moments. The thin plate has to do with how we can analyze the volume of an object and make use of some of these areas that we already knew. 3D bodies, obviously, is the next, and then composite areas, tables, right? Composite areas, tables. Right, so what is the mass moment of inertia? By definition, it is still the moment of inertia. In this case, instead of our dA, which was for the second moment, we are now replacing it with a mass. So consider a mass, consider an object such as this one, which is on which you apply a couple, right? If you apply a couple, which is noted by that arrow, that couple is making the object to rotate, or is giving the object a tendency to rotate about the A prime axis. If we had just one of the particles that make up that object, it's obvious that we would find the mass moment of inertia using our equation. I is equal to what of integral of r squared dm, where this would be our dm. So now if we have a complete object, it's obvious that we need to sum them up, hence the integration. And then if we were to concentrate this mass, this is mass m. It's made of delta m1, delta m2, m3, and so forth. If we're to concentrate it into just one mass, guess what distance we should locate it at from the axis? That radius of gyration. So we still have the same concept. So the radius of gyration is equally defined as k is equal to the square root of I over m. So our moment of inertia is our I is equal to integral of r squared dm, and our radius of gyration is still given as before. Now, remember that we are in 3 dimensions this time because we're looking at some mass, isn't it? We are in 3 dimensions this time. So let's assume that our dm is located, or our mass element is located at some x, y, z location. At some x, y, z location. So it's located at some x, z, y location, right? That's our mass element. So it means that if we want to find the mass moment, let's start with the y-axis. If we want to find the mass moment about the y-axis, our equation, remember our equation, it's giving us this format. And what is this r? What is this r? It is simply that distance from the axis of rotation. So if we want to look at that distance, obvious, from the y-axis, so we are looking at IY. So from the y-axis, we have some distance r. This means our integral would be the integral of r squared dm. But what is r squared? If you look at this triangle, our r squared is equal to x squared plus z squared. So this means that we would substitute this into that in order for us to come up with equation 930, the IY equation. So basically what we are seeing here is we need to interpret the distance from whichever axis into its constituent components. So basically we now have an IY, or the moment about the y-axis, which is equal to r squared. The r is from the y-axis. So therefore the r can be written in terms of the x squared and z squared using Pythagoras theorem. That basically summarizes the definition of the mass moment of inertia about the y-axis. The same applies then for the x-axis. If we want the mass moment of inertia about the x-axis, then it means we are looking at the distance of our mass moment from the x-axis. So if we look at the distance from the x-axis, then we should then use the following. If we use it from the x-axis, so let's say it's this, isn't it? This is the distance from the x-axis. So what is that distance made of? It's made of some z and some y component. So it's made of some z and some y component, right? It's a bit tough for me to draw it here, right? It's a bit tough for me to draw it here because we're looking at this x distance, right? So this x distance will be obviously parallel to that, and then we have our x and our z, our y and our z. So for that reason, we have our y and our z in there. For this y, I, z, we've got our x and our y. That defines the mass moment about the x, y, and z axes. The second concept we will extend to the mass moment regime is the parallel axis theorem. The parallel axis theorem, we already knew it before. So in terms of areas, we knew that we need to first draw some centroidal axis, because the parallel axis theorem always relates the moment of inertia of some area to the centroidal moment of inertia plus what? Plus AD squared. So if we are to look at a new centroid, in this case, since it's some object, let's call that centroid the center of gravity. This is where we are aware that this material should have the same what? Rho, or it should have the same gamma. So let's assume, remember that if it is not uniform, then the center of gravity is not necessarily the centroid. So if we are to look at centroidal axes, x prime, y prime, z prime, right? X prime, y prime, z prime. Those centroidal axes, centroidal axes are a distance x bar from the z axis. They are a distance z bar from the x-axis and a distance y bar from the xz plane. Those are our centroidal axes. So if our centroidal axes are located there, this means we can find an absolute position of our mass element. We can find the absolute position of our mass element if we are to locate it in terms of x at some x prime position, and also in terms of y at some y prime position from the centroidal axis. Therefore, its absolute x using the original reference frame is given by the centroidal x, which is our x bar, plus the x prime from the centroidal axis to the mass element. The same applies for our y and our z axes. Now let's recall our equation. Our equation told us that the mass moment Ix is given by y squared plus z squared integrated with respect to mass. Now let's substitute, because we know y squared and our y is this. So if we then take it into the equation, or if we just plant it in there, then it means we've got our y prime plus y bar all squared. The same applies. We will add a z prime plus z bar, then all squared, and we integrate with respect to mass. So we can expand the bracket, right? We can expand the bracket. When we expand the bracket, we're expanding this one. So I think we are aware already that our y prime z prime, this must multiply, right? So we've got our y prime squared plus 2 of what? Y prime y bar, and then plus y bar squared, isn't it? So that makes the first bracket. So that will be our y prime squared plus z prime squared, right? So this is obviously coming from that term there. The bars that were squared, they add up and they are there because they are constants, which means we can group them together. Then the second terms, which were 2y prime and 2z prime, these are all also gathered together. But what do you see here? What do you see here? These are the first moments about centroidal axis. So this is about the centroidal x-axis. This is about the centroidal z-axis. Centroidal y-axis, centroidal z-axis. So if we have these moments, then it means that these will cancel out, and in the end we will have this first equation. So if you still remember, our format of the equation for the mass moment is like this. So if it's with reference to a centroidal axis, then it's obviously this is obviously representing the centroidal mass moment of inertia Ix prime. Right, so when we have Ix prime, these two had annihilated to 0, so it means our last term is basically there. If we integrate dm, we will get a mass. So for this reason, our parallel axis theorem, right? Our parallel axis theorem for mass moments reads as follows. Our Ix is equal to the centroidal mass moment plus m y bar squared plus z bar squared. For Ix. For Iy, we would have z bar squared plus x bar squared. And the same applies for Iz. Now look at these distances. Look at these distances. Z bar squared plus x bar squared, for example. Z bar squared is this distance. X bar squared is this distance, right? Those are the two distances that we are considering. Also consider, for example, z bar squared plus x bar squared, right? There is a Pythagoras theorem that we are actually seeing in what's happening here. There's a Pythagoras theorem that we're actually seeing in what's happening here. The best that would explain it is this yx triangle. As you can see, we've got a yx. So if we are to look at these this centroidal axis and the original axis from the arrow that I've shown there, we would see For example, the centroidal axis at that point with the original axis at that point. So that would be, it's what? It's y, and then it's z, it's looking at us, and then its x is in that direction. The centroidal axis will be located here. Its y would be obviously there, its x would be there, and its z would be looking at us. So this would be now our y bar squared. This would be our x bar squared. So, this is y bar and x bar. So this obviously means that we can find this distance between the two axes that are looking at us, right? So that becomes our d. And we can tell that our d squared would be equal to x bar squared plus y bar squared. So basically the distance d is the distance, perpendicular distance that is in between the parallel axes. For this reason, we have an interpretation of our moment of inertia in the parallel axis theorem to be equal to our I, let's say it's for the x being equal to the centroidal plus md squared. The d in this case would be for the ix, it would be between the y squared and the z bar squared axes. So that is how we can interpret the parallel axis theorem. So by convention, and I'm sure we've carried out these calculations, so I'm sure you can see that we can actually end up getting this equation of the radii of gyration, isn't it? This would be the centroidal radius of gyration, and then we've got our d squared, and then we've got our k squared. That's equation 9.34. So we've introduced the mass moment of inertia, as in the integral of r squared with respect to m. Then we've introduced the parallel axis theorem for that mass moment. Now let's talk objects and see how we can actually interpret or convert areas into actual objects. So we will then look at mass moments of inertia of thin plates. So a thin plate is an exciting piece of material because it introduces to us the concept of area and thickness, so that we get some volume, which is equal to what? The area multiplied by the thickness. And one of the most important parameters to use would be, let's say you're in the SI system, the density is equal to the mass over the volume. So obviously, this would imply that our mass is a density times the volume. The volume is what? Is the area multiplied by the thickness. So these equations would then help you to convert our previous equations into equations with the density and the area. Why are we trying to convert to the area space? Because we know the area space, isn't it? You've used the area space, you know how to find mass moments of inertia in the area space. So you can go back to that area space and use it. Right, so in figure 9.24, we have a thin plate with an axis A prime. So that's our thin plate. This is our axis A prime. Right, so we've got another thin plate with an axis B prime. We've got the same thin plate now with all axes shown, right? A prime being a vertical axis, B prime being some axis normal to that vertical axis, and C prime being a centroidal axis, right? So C prime is perpendicular to the plate, right? So it's passing through point C. Now, if we would like to calculate the mass moment of this thin plate about the A prime axis, it's obvious that we would need the distance to that A prime axis. For what? For some small mass element. So this would be, let's say, our dm. Let's say this would be our dm, and it's a distance r from the A prime element, A prime axis. Now we know this is our equation. So how then do we use this equation? How then do we use this equation to interpret this object in terms of what we know, which are moments of inertia of areas, or second moments. Now, what we will do is to then rewrite our dm. Remember, if we have our mass being equal to that, this means our dm, the rho doesn't change, right? Our dm, the rho doesn't change. The thickness, this is the thin plate, doesn't change, but our dA is what determines the dm. So if we are then to replace dm with rho t dA, what we have is rho t, but then we are going to obviously integrate that to get some area. So in the integral, we now have what? R squared dA. And guess what? This, I think you still remember, the integral R squared dA. Remember, our R squared in this case is simply the distance from the axis, right? It could be a y-axis, so that it becomes what? It could be x squared dA. It could be an x-axis, so that it becomes a y squared dA. But in this case, it is what? It is an r squared, so it's simply representing that distance from the axis. So this is our integral, and we can tell that, okay, this one is just a mass moment, sorry, this is just a moment of inertia about the x-axis, but this is a second moment. So in actual fact, our mass moments are a function. They're proportional to the area moments. So this is the reason why we were studying all those area second moments, so that we can interpret the second moment in terms of area into the mass moment. Then when you have some heavy object, all you need for a thin plate, for example, is the density of the material, the thickness of the thin plate, and you carry out your usual integration. That is the meaning of equation 9.35. 9.36 by the same method is simply looking at the B prime axis. So obviously you would need to find your distance of the mass element from the axis, so that you can calculate your moment of inertia about the B prime axis. The same then applies for your C prime axis, and in this case, I guess you can tell that if the C prime axis, remember we said we are looking at what? If our object is located at some distance there, and this becomes a radial distance, that actually becomes the polar moment about the C axis. So if it is the polar moment, then it means it is a sum of the of the AA prime and the BB prime axes. So these equations are simply converting from the area moments to the mass moments by multiplying the moment of inertia, or the second moment, by rho t. Right, so for us to then, let's look at typical geometries. Let's look at typical geometries. In this case, you're looking at thin plates. So let's look at a rectangular plate. This rectangular plate in figure 9.25, it has some length A, so that is its length. It has some width B, and it has some thickness T. So that's our rectangular thin plate. This thin plate has some axes drawn around it. So we've got the BB prime axis, and we have the AA prime axis. The BB prime axis is horizontal from what we can see, let's say from this angle, and then the AA prime is vertical, and the CC prime axis is at right angles to the plane of the rectangular thin plate. So let's have some definitions. The mass moment of inertia, about the AA prime axis can be calculated. The mass moment of inertia about the AA prime, from what we have already found out, we can still use the rho t and multiply by the area moment of inertia, or the second moment. Now, what is the second moment of a rectangular thin plate, or of a rectangular geometry? In other words, we are now looking at the rectangular geometry only. So let's look at the rectangular geometry. What I'll do is I'll pull out those tables that we had before for mass moments. So let's just see if we have the tables here. Right, so these tables, let's make them large. These are from figure 9.28. So these are from figure 9.28. You have them in your textbook. So let's just look at the rectangular thin plate. Okay, sorry, these are mass moments already. Okay, so I need to actually use this because we are looking at area moments. So we are using figure 912. We are using figure 912. So let's use it and see. Let me just see if I can also comment. Right, so this is the rectangle area. This is the rectangle area. In our case, the x prime axis, the x prime axis is actually a what? A b prime axis. In our case, the y prime axis is actually the a prime axis. We want to find the moment of inertia about this axis, because according to our drawing, this is the what? This is the a prime axis. So let's just recall that. Remember, this is our drawing. So according to the other table that we saw there, this would be the y prime axis. Remember, it's passing through the centroid. So let's find the centroidal y-axis y moment, the centroidal y moment. So the area moment of inertia, the second moment about the y prime axis is given there. So this is the moment of inertia about the y prime axis. Moment of inertia about the y prime axis. It is a 12th of b cubed h. It is a 12th of b cubed h. So let's first interpret the following. The b is the base. The h is the width, right? The b is the base of this rectangle. The h is the width of this rectangle. Let's look at our rectangle. Our rectangle has a base. So this is its base. And then this is its what? Its height. So this means when we said the y prime centroidal is equal to what? A 12th of b cubed h. This means that if we are to interpret it into our diagram, 1/12, the b is the base according to our previous diagram, so that would be, in our case, a cubed. The height was the h, I will call it b according to our diagram. For this reason, we will use this as our IAA of the area. This is the reason why our equation, is there a number there? Okay, so it's part of some set of equations. So this is why our equation for the mass moment of inertia simply reads IAA of the mass is equal to rho t multiplied by the IAA of the area. So our rho t is still there, and then our IAA of the area, the given area, is now this 1/12 of a cubed b. So remember when we talked about the orientation of, we're talking about orientation of angle ions, right? So this is the same thing. So you need to check and see if the angle ion, its orientation is the same as the orientation that you're given in the question. And then you also look at its dimensions. So this time our A and our B have actually been what? Have been, our B and our H have been replaced by an A and a B, but the B is not the same, right? So you need to look at it according to what's given. Right, that's our AA prime, we're sorted. By the same method, our IBB prime mass, right? Mass moment is our rho t multiplied by the area moment. So it's a matter of just you pulling out the area moment. So that's our area moment there, and then we're looking at the BB prime axis. We can see that the BB prime axis resembles what? It resembles our centroidal axis from the tables. So let's go back to the tables. Now we're happy with this one. We want about the x prime axis. Centroidal about the x prime axis. So what we're getting is we've got a 12th of b h cubed. A 12th of the base height, which is the width cubed. So let's now reinterpret it here. So we said our ix prime is actually equal to a 12th of bh cubed. So it's now the reverse of this, so we can obviously just replace. Our b, we said, is the base, so that's an a. Our h is a b in our case, BH cubed, AB cubed. For this reason, we have a 12th of AB cubed. So I think now you can tell that our mass moments are simply area moments scaled by rho t, right? So this is not much of a difference. What's most important are the geometries and interpretation of the labels. So now we have our mass moments. So then, since we know how we can find the actual mass of this object, then we should be able to interpret it in terms of mass m. So we're now converting back. So what did we do? We wanted to find the mass moment, but we wanted to integrate r squared dm, but we don't have to worry about that because we can convert to area moments. We know how to do that for regular shapes. We have all the mass moment, the area moments, as many as we need. So because of that, then we can carry out our normal area moments, and we've got an expression. Now we also know how to get the mass of what? Of a rectangular thin plate. What is the mass of a rectangular thin plate? The mass of a rectangular thin plate is simply equal to, we say density times volume. So what is its volume? Volume is its area multiplied by its what? Its thickness. So we now have our rho t already. What is its area? So we've got rho t, then it means this part for the mass is already supplied. What is the area of this rectangular plate? It's simply AB, isn't it? It's simply AB. So if we take out rho t AB, we now actually have written the mass. So this means where we had I A mass being equal to rho t I A area. So let's now write it as rho t multiplied by a 12th of a cubed b. We want to take away a b, isn't it? So that will be equal to rho t a b multiplied by 1/12. We've taken out an a, so this means we will have an a squared. We've taken out a b, then we're done. This means that this is actually representing the mass. This is representing the mass. So that is why it's now mass 12th multiplied by a squared, or a 12th of m a squared. So therefore you now have your mass moment of inertia about the AA prime axis as a 12th of m a squared. The same applies if you carry out that math, you will get that for BB prime. What did we say we find from ICC prime? That is the polar, isn't it? So the polar would basically be the sum of the two. Since we already have the terms in terms of mass, then we may as well just add them up. So that becomes your moment of inertia about the CC prime axis, which is into the area. Right, so I think okay, so the same can be applied for the thin circular plate, figure 9.26, right? So our mass moment is the same equation. This one, if you go to your tables, you would find that about a vertical centroidal axis, that is your moment of inertia of the area, second moment. So maybe you can just verify that. Circle, there we have it. The y in this case is actually our centroidal moment of inertia, which is this one. That's why we have a quarter of r to the 4. A quarter of r to the, pi r to the 4. So basically you follow the same method, and this one would also apply for IBB prime, and then you will add them up to get your ICC prime. Right, so let's look at an example. Right, in this example, a thin plate with a mass m is cut in the shape of an equilateral triangle, side A. Right, so we have side A on all these sides. Determine the mass moment of inertia of the plate with respect to A, the centroidal axis AA prime and BB prime, and then the centroidal axis CC prime that is perpendicular to the plate. Right, so we want to find the mass moments. So obviously, the I mass about the AA prime. Maybe let me move this word. The IAA prime mass would be equal to, we now know that it's simply rho t, and then IAA prime of the area, IAA prime of the area, which is the second moment. Right, so this would be rho t of what? What is the mass moment? Sorry, what is the second moment of a triangular area about a vertical axis? So this is our vertical axis AA prime. So let's jump onto the tables. We are looking for a triangle. Jump onto the tables, looking for a triangle, area moment, triangle. There we have it. So we've got a triangle. Right, this triangle is, it has a base B, it has a height H, it has this as the centroid position, like we said, a third of what? Of the height. Then we only have a moment of inertia about the centroidal x-axis and a moment of inertia about the base axis. So the moments of inertia that we're given are for the centroidal axis and the what? And the base axis. Let's look at this triangle that we have and this AA prime and see what it means. This AA prime axis, it's BB prime is the centroidal axis, so we actually can easily find our IBB prime. But IAA prime is a centroidal axis in the vertical, but from the areas that we were given, we do not have an I about the what? The Y. So what do we do then? What we are given though is a area moment about a base, right? An area moment about a base. So we can actually reinterpret this triangle and take advantage of the base area moment, because that's all we have. So if we are to draw our AA prime axis, let's say horizontally, we could actually have one part of the triangle forming a normal axis that looks like what we have in our tables, right? So we actually have this base axis. So this is one of the triangles. Let's say it's this one, then this would be the second one, which means all we need is just twice of whatever area moment that we get about the base. So this is our new base. This is our new base. Its dimensions, we need to find out what is its dimension. What we know is that this side is an A. That's all we know, right? We know that this side is an A, so if that's area number 1, this would be the side that I just labeled A. The base is AA prime, so that is the base. Then this side, we do not know it. In fact, we know it. It's half of A. This is half of A, right? Yes, this side is half of A. So we now have a half of A there, and we have some angle. This is 30 degrees, isn't it? This is 30 degrees because we are bisecting the 60 degree of that angle. Right, so I think we now have some grounds to use our equation for the area moment relative to the base. So let's look at the equation and see what is necessary from that table. The table says the mass moment is given as a 12th of BH cubed, a 12th of the base times the height cubed, a 12th of the base times height cubed. So in this case, we would have the area moment about the AA prime axis is actually equal to a 12th. What is the base? We need to find this base. This base is actually this height here. It's actually this height there. So how can we find it? We can use this angle, isn't it? We can use this angle because we know we can do some geometry. So if we use cosine, for example, cosine of 30 degrees, cosine of 30 degrees is equal to this base that we are looking for over A, isn't it? This base that we're looking for over A, which implies that this base is actually A multiplied by cosine of 30 degrees. And what is cosine of 30 degrees? if we could write it, we know it's 0.8660. So that would be, let's say, a multiplied by root of 3 over 2, isn't it? Root of 3 over 2. So that's our base. So we now have the equation. It says a 12th of the base, right? Okay, so this calculation, I was writing it right here. So this is what I was just scribbling there. So we now have the base. We know the base is what? Is a root 3 over 2. So this would be a root 3 over 2. So we now have it there. What is the second part of this moment? It's an h cubed. So we need to cube the h. In our case, our h is actually half an a, isn't it? Our h is actually half an a. So that would be a over 2 all cubed. A over 2 all cubed. This is the area moment for just one part of the triangle. For one triangle. So we are now writing it here. 1/12 of what? Of a root 3 over 2. Of a root 3 over 2. Multiplied by what? By a cubed over 2 cubed is 8. A cubed over 2 cubed is 8. Okay. So we now have this whole range of parameters to think about. So, okay. So let's just now see that we said we need 2 triangles, isn't it? We said we need 2 triangles. This is a mass moment of inertia in total for the whole triangle. This that we calculated for is just for one triangle. So we need to multiply this by 2 to have 2 triangles. So if we then do the math, this 2 can remove that 2, and our equation can simplify into this. Our A prime mass is equal to our rho t multiplied by 1. Okay, we can actually say root 3 over 12, right? Root 3 over, what is your 12 times 8? What is your 12 times 8? I think it's a 96, right? That should be 96. So root 3 over 96. The a's are now becoming a to the 4. That's our I mass. Multiplied, so we are happy. We've got our I mass, but our I mass is in terms of a4, a to the 4. The question requires us to state this I mass in terms of what? Determine the mass moment of inertia with respect to, okay, we're just determining the mass moment. Okay, so we can actually write it in terms of mass, isn't it? In terms of m. What is m? How can we get m in this case? How can we get m? So we know that to get m, our m is simply equal to, rho multiplied by volume. Rho multiplied by volume. So what is our volume? Our volume is area multiplied by thickness. So we've got our rho t. The area of a triangle is half of the base. The base in this case is an a, isn't it? The base is an a. Half base times height. The height, we found it as that root 3 over 2 multiplied by a root 3 over 2. So this is our area. Right, so how can we then remove that? Okay, so obviously for you to then put this as an area, you can simply divide this by that. It means now you will have the mass. In other words, we want to factor out rho t and then multiplied by root 3 over 4 a squared. We want to factor out, so let's just write it this way, rho t a squared, then root 3 over 4. If you factor that out of this equation, then you've got your what? You've got your mass. Right, so the rho t part can be factored out. What would we, and the root 3 can be factored out, okay? And the a to the 4, okay, we'll remain with a squared. So we'll remain with an a squared. Then if we factor out, what is 96 divided by 4? What is 96 divided by 4? Whatever factor we remain with is divided by, okay, let me just use a calculator here. So that would be 24. That would be 24. So that would be what? A squared over 24 is what we remain with. after we've factored out our mass. So it's simply a 24th of ma squared. A 24th of ma squared. Okay, I think for BB prime, I don't need to waste time. We know that our IBB prime is equal to, okay, rho T, this is mass, rho T IBB prime area, second moment. Right, rho T IBB prime area. BB prime, let's look at BB prime. Centroidal, isn't it? Centroidal, horizontal, parallel to what? To the base. So we just jump onto our tables. The tables tell us that parallel to the base, this is exactly where we are, right? But we want the centroidal. So we want this one, right? This one is a perfect match. It's simply exactly where we want it. We want the centroidal axis, which is some height. We don't care. It's just a third of the height from the base. But it's a centroidal axis, and we want this moment of inertia or second moment above the centroidal axis. So it's a 36th of BH cubed, B being the base, a 36th of BH cubed. So we know then that rho T multiplied by a 36th, B being the base, our base we know is A. H cubed being the height, we already calculated our height. It was what? It was A root 3 over 2. A root 3 over 2, and this height is what is cubed. So let's just verify that. Yes, a 36th of BH cubed. So a 36th of B, which is an A, H, which is that cubed. So we're happy. So I think it's a matter of you now doing your math. 1 over 36 multiplied by A to the 3. This would be obviously 3 root 3 over 8, isn't it? 3 root 3 over 8. And then you can, the rest is history. Right, what did we want to use? We said the mass is a what? The mass is a rho T A squared. So we have an A to the 4. Let's just simplify this. Actually, let's write this in terms of what? In terms of this, right? So that we can extract it. Oh, maybe let me do it here. So this is now equal to rho T, right? Multiplied by A squared, right? So if we take an A squared, we remain within A squared. Then root 3, which means we remain with a 3 over 8. We remain with a 3. At the denominator, we want to extract a 4. So which means we can remain with a what? With a 36 multiplied by a 2. 36 multiplied by a 2. So I guess a rho T A squared root 3 over 4, isn't it? A squared root 3 over 4. So we've taken out an A squared. We're happy. I think we're good. So this must then represent that mass M. So that's our mass M. Once again, rho T A squared root 3 over 4. The rest is history. So 3 there, 3 into 36 is a 12th. So we've got another 1/12. Okay, so looks 1 over 24. Looks the same as what we had before. Ma squared. Right, I think that's okay. The geometry and the algebra will not lie. So it's another 1/24 of ma squared. So the last question, they want us to calculate the CC prime. We know that is just a sum of the two. So 2 multiplied by 1/24 would give us a what? A 12th of ma squared. That would be your polar moment. Right, so I think the use of your tables is coming in handy now. Now let's move to the fourth concept. The fourth concept is on moments of inertia of 3D bodies. So if we have some geometry that is, some body that has an analytic function that defines its geometry, then we can now take advantage of our integration. So the moments of inertia of 3D bodies the 3D body would be described by some mass element, and then we can scale up the mass element. So this mass element that we need to integrate is obviously given by so we had that equation, right? We had that equation. Where was it when we introduced this? There we have it. Our mass element is what? Is rho T dA. Our mass element is rho T dA. So let's just take that all the way to this set of equations. So there we have our mass element. Can I just paste it here? Right, so that's our mass element. Our mass element is rho T dA. Our dA, obviously, in this case. So we first of all have a rho, isn't it? We first of all have a rho, so that's our rho. And then our thickness of this plate, our T is actually dx, isn't it? This is for the mass element. Then our dA, the area. So which means in this case we actually have dt, isn't it? We actually have dt because we've got a what? An area which is defined by an analytic function. So this is our pi r squared, right? That's our pi r squared. So which means we can now write our dm in terms of rho pi r squared according to this geometry, right? Remember, this is for this geometry. Pi r squared dx. So we now have our element of area pi r squared, and then our dx is the thickness of this mass element. What is our small ix which we will need to integrate? Let's say we want to find the mass moment about the x-axis. So our small ix is obviously half r squared. Where are we getting this? So back to your tables. Circle, there we have our circle. Right, so there we have our circle. So in fact, we'd actually done it. We'd used the circle already. So we actually have a result from this analysis. So this is what we have. Okay, so for the C prime axis, our di would then be equal to half of r squared dm. This is the reason why we have our equation there. It's already been converted into the mass format. So that's our dix, which is now making use of this dm, so we can now substitute it. Parallel axis theorem, what does it say? Remember this plate that we want to integrate, we can actually interpret it in terms of the parallel axis theorem for the y direction, Why? Because it is actually displaced from the y-axis. It's actually some distance from the y-axis. So obviously the moment of inertia would be d about diy, which is about the y-axis, being equal to the centroidal. So this would be the distance of the centroid from the y-axis, plus x squared dm. So our centroidal diy, we know it, right, which is a quarter of r squared, and then plus the x squared, which we've just identified with respect to m. So I think this one is a matter of just converting from one system to the other. In the iz, by what distance is it from the z-axis? So from the z-axis, we still have a distance x. So that's why our iz is also looking like the iy, because both axes are some distance x from this element. So now when you have defined your area element in terms of where it is located, then you can integrate away to get your mass moment. Right, so if you have an equation like this dv, you can use calculus. So you can use double integral, triple integral, whichever you want. But you can actually make life easy for yourself if you just use some volume element which varies in one direction. For example, here, as long as we have symmetry, then it means it makes sense to just use that element in the integrated with respect to x. Right, an example is shown here. We've got some question on moments of inertia of 3D bodies. So the area shown is revolved about the x-axis to form a homogeneous solid of revolution of mass m. Okay, so we'll rotate this about the x-axis. Okay, fine. So using direct integration, express the mass moment of inertia of the solid with respect to the x-axis. Express the mass moment of inertia of the solid with respect to the x-axis. With respect to the x-axis. Right, so let's see. If we were to rotate this about the x-axis, what kind of an area element can we come up with? So let's see if we've got an x-axis there. And then, okay, so we'll end up having something like a cup, isn't it? Can I just draw this, and then since it will rotate, the area element will look something like this. And let me just make it a disk, because this is a volume that we're going to end up integrating. So this volume, this area element has a thickness dx. This is its starting point, y is equal to h. This is its end point at a, where y is equal to 2h. This would be y is equal to 2h. So already, can you see something here? Can you see something? This radius is actually a function of y, isn't it? It's actually y as a function of x. So what does this mean? This means that we can define our dm as usual. Let's define our dm, which is the area element. So this is a what? This is a disk. If it's a disk, we had our dm already defined, half r squared dx, isn't it? Is that so? Let's just see. Yes, half pi r squared dx, sorry. Half pi r squared dx. And we know that in our case, how can we find our r? How can we find our r? Our r is a function, isn't it, of y. So what is this function? The function will be r is equal to y is equal to mx plus c. What is the gradient? Y is equal to mx plus c. What is the gradient? The gradient, sorry, what is the slope? The slope for this function, the slope is obviously, let's call it m, is equal to the change in y over the change in x. Change in y for this line is obviously, okay, so it's actually an h then. So it's just an h over what? An h is 2h minus h. So it's an h over the a. An h over the a. So this is equal to h over a. That's our slope. So obviously this would be h over a multiplied by x plus the h, which is the height, or the intercept rather. It's the intercept. So obviously this is now equal to half of pi multiplied by this function h over a x plus h squared dx, right? Squared dx. So you can actually make life easier for yourself mathematically, so that this whole function, it won't look too cumbersome. So that's your first thing. So then our dix, we can now express our dix. Our dix is for a disk, which is a circular disk. So I think it makes use of the same setup that we had here, which is just half r squared dm, right? So that's half r squared dm. So this would be half of r squared. R squared is the function squared. So we just want to square this r. So that's our h over a x plus h, all squared. dm, we already have it here. That's a half of pi into h over a x plus h all squared dx, which means therefore that your ix is the integral. I think these constants can conveniently be removed. So we've got a quarter here. We've got a quarter here of what? Of pi, isn't it? A quarter of pi. Integral of h over a x plus h. This multiplies the other one. This is raised to the 4. Dx, and our dx is from 0 up to a. Right. So there you have your mass moment. So this means that when you now have, you need to then find the mass, because we want to write it in terms of m and h, right? So this one you can integrate away and have fun. So in terms of m and h, in terms of m and h, it means we need to find m. We need to find m. So how can we get m? So that when we have the expression for m, we factor it out of this whole integration result. We knew already that our dm is what? Is half of all this. In other words, okay, in other words, we're just integrating this, isn't it? In other words, we'll just integrate this. So let's just copy that. Let's just copy that and integrate it. So let's paste it here, paste it there. So all we want is to integrate this term. Let me move that. So we'll just integrate dm to get the mass from 0 up to a. So in this case now you have a mass which is equal to some function of a and h, isn't it? Then in your result you factor out that function of what? Of a and h. When you take out the a and h's, then you will actually remain with some mass and some h. Probably the a will disappear, most likely, according to what they say. So the a should disappear. Okay, so that summarizes your what? Your integration method. How would you perform the integration? You first need to define your mass element, then you define your moment of inertia, the small contribution of the moment of inertia. Then you integrate that according to the variables that make sense in your integration. So the section on mass moments of composite bodies is now just the use of your tables, right? So basically here, what has happened is your bodies have already been resolved. So for example, a thin rectangular plate, we had a calculation earlier, right? We had a calculation earlier. So let's just see if the calculation was true, because we actually have a result. In fact, we got a result using the textbook. So let's just see how it relates to this. So that's a thin rectangular plate. And they say the mass moment, for example, about the, okay, right. So there are a lot of things here. I need to be careful with what I'm reading. About the vertical centroidal axis, it's rho t. In fact, okay, let's use this result. Let's use this result. So let's just transport this result. The I, usually that would be the what? The vertical axis. So let's say centroidal vertical axis is 1/12 of ma squared, where a is the base. So a is the base of the thin plate. A is the base of the thin plate. So let's just take this result and make use of it and see if downstairs it makes sense according to those tables. So here we have it. Let's see, our thin rectangular plate has a base C. So I'll just paste this result from what we had before, paste it there, right, and just remove this. So they said I about the y. Fortunately here our y-axis is also passing through the in this case, we actually have a center of gravity, G. Let's hope it coincides with the centroid. Right, so they say I about the y is 1/12 of mc squared, c being the what? Being the base. So I think it's making sense. Our c in this case is the base. So it actually agrees. So this part is fine, which means that our tables make life easy for ourselves. So don't forget that when this thickness becomes large, and it becomes actually a rectangular prism, then it's a different story. Please don't forget. So make sure that you can understand the geometry of what object you are dealing with. Right, so that summarizes composite plates. When you have some plate, just decompose the area, the plate, into the regular geometries that we see in table what? In table figure 9.28, in data sheet of figure 9.28. Right, so this is how you would then apply this principle in example question 9.142. Determine the mass moments of inertia and the radii of gyration of the steel machine element shown with respect to the x and y axes. The density of steel is given. Right, so if we have such a shape, if we want to find the mass moment about the x-axis, we need to what? We need to... Right, so here I think... Okay, so we need to demarcate this object into different geometries, because what we have in our tables, we don't have that kind of a geometry. Like, it's just one geometry. We don't have that kind of a geometry. This is our table 9.28, right? This is our table 9.28. That's the label there. So if you look at the geometries here, we don't have something like what we had in our question. What we have is some portion, a rectangular prism, and what else? I think that's all we have, isn't it? We also have some circular cylinder. Okay, so we can actually decompose it. We can decompose it. We can decompose this thing. Right, so how can we do it? Let's decompose it and see how best we can do it. So we've got, let's call this is a cylinder, right? So we've got, at least we know that we had a cylinder in our tables. We've got a circular cylinder. This area is negative, isn't it? So we can actually use it. So this is also a what? A cylinder. Then what would happen? Okay, for this we can actually make a what? A rectangular prism, isn't it? Up to these half moons, up to these half moons, we can actually use a rectangular prism. So we can actually call this some other area, a rectangular prism. It's not a thin plate, right? It's not a thin plate. So rectangular prism. As long as it has some dimension for its thickness, then it's a rectangular prism. Then if we have that, then what about these half moons? What can you do with these half moons? What can you do with these half moons? If we join the half moons, they become a cylinder, isn't it? If we join the hemispheres, they become a cylinder. Right? So remember, we are thinking, we've already defined this. This is going to be subtracted because we know the area is a negative area. So whatever mass moment of this is going to be subtracted. So these two half moons, these two hemispheres can be joined into one area. So we can actually call this another, this is a cylinder. So let's call this cylinder number 1. Cylinder number 2 will be removed. Cylinder number 3 will be made of 2 cylinders. Cylinder number, in actual fact, we could call it half a cylinder, right? We could call it half a cylinder. And then rectangular prism can become area number 4 and so forth. So when you have done this, this means that your mass moment Ix would be Ix of area number 1 plus Ix of area number 2 plus Ix of area number 3 and so forth, and you add them up. Take an example. Ix of area number 1. Ix of area number 1 is the what? So this is our cylinder. So this is our cylinder. Now by virtue, cylinder number 1, right? This is for cylinder number 1. Look at cylinder number 1. We want the mass moment about the x-axis, but this cylinder is actually offset from the x-axis. Its centroid is offset from the x-axis. This means we'll need to use the what? The parallel axis theorem. This means we'll need to use the parallel axis theorem. Plus, what did it say? Md squared, isn't it? Md squared. So what is its centroidal moment of inertia? And then our d, we now know that our d is going to be the distance from half of its thickness, which is actually 20 all the way up to there. So we have this first 20, the second 20. So our d for cylinder number 1 is actually 20 plus 20, which is actually 40 watt. Distance is in millimeters. So this d is 40 millimeters. The mass, we know that the mass is simply equal to the density times the volume. We've been given the density, so we will use that. The volume is what? Is pi r squared. The r is given a 44 times the thickness or the height, which is a 40. So you've got all the dimensions. How about the centroidal moment? There you can now go to your tables and make use of that. So let's jump onto these tables. We've got a circular cylinder. About what axis are we looking for this mass moment? About what axis are we looking for this mass moment? This is about the x. So centroidal x-axis. Our centroidal x-axis is actually penetrating, it's like a diameter, isn't it? Through the centroid. Our centroidal x-axis, the one that we are using for this parallel axis theorem, is through the diameter. So we want a diametric centroid. That is what we're looking for. So the diametric, what we can see here is the y. According to the given data, it's a what? It's a y. So if we want to find, and this y is through the centroid. So if we want to find about the y and also the z, because they look symmetric, right? So we will use this iy, which is actually given as what? So let's just zoom out there. It's a, okay, so that's a long term. So it's a 12th of m into 3a squared plus l squared. Right, so we need to interpret this now. What is a? A is the radius. What is L? L is the length, right? So let's not forget that A is the radius of this cylinder. So let's now write that term in our equation. We know that the centroidal, we are going to add md squared. So we are going to write it, so let's just write it here. We have the centroidal 1/12 of the mass. We know we can calculate the mass. So actually let me write it as what? As rho pi r squared h multiplied by, right, r squared h, let's be careful. H is actually L. H is actually L according to the geometry that is in there. And then this would be your radius. So we're actually happy with that. Then we are multiplying this by 3a squared. 3, our a we said is a radius, so it's radius squared plus an l squared, which is simply the length. So I was just putting this to represent that this height, according to the table, is actually given as L, plus the mass md squared, so that's our rho pi r squared h, and we said this is an L of the cylinder, and then this is multiplied by what? This is multiplied by d squared. So our d squared, I think we've already identified that d. So that would be your example area number 1 about the x-axis. So the same applies for the y-axis. For the y-axis, you actually use the centroidal. Can you see that? For area number 1, you need the centroidal moment of inertia again, because it is what is displaced from the y-axis. So centroidal of area number 1 about the y-axis, that would be plus another m. This is now our d in the y. So let's just call it d in the y. Let's call this d in the x. Sorry, d for the x. So d is actually, okay, so this would be, I'll call it d for the x, right? So which means you need to be consistent with your labeling. So I'll call this was the d about the x. The d about the x. So md about the y squared. So you do the same. Your centroidal, we already know it. Now we are looking at about the y, isn't it? Centroidal about the y. The y is through the what? Through the center of that circle. So if you come to our tables, the center of that circle is actually the x. So we're actually using this. So it's half m times r squared. Half m times r squared. So that's actually equal to half of the mass times the radius squared of that circle. The mass, we already have some terms that we had there. The mass was rho pi r squared times length. Rho pi r squared times the length. That was our mass. Then we say times radius squared. Then plus that same mass, rho pi r squared length, multiplied by d in the y squared. Then you would calculate that. That would be for the disk, for the circular disk, for the circular prism there. Right, so I think this is now a matter of extending the same to all these other geometries. You're extending the same to all other geometries. You're simply using the other circle, the other, what you call it, let's call it a cylinder, which is the empty cylinder. You're doing the same, but you are subtracting it as far as your mass moments are concerned. you're subtracting it because it is an empty area. I think we had already discussed how to interpret that. So when you add all these up, all your IYs, you get your total IY. When you add all your IXs, you get your total IXs. Your radii of gyration, I think this one is straightforward. You already have an equation. IX over the mass this time. And then obviously your K about the Y would be the radius IY over the mass. So please don't forget that this time it's over the mass. Right, so I think this sums up our discussion that was mass moments of inertia. Basically, with mass moments of inertia, what we said is, in mass moments of inertia, we are making use of the area second moments, because we can simply scale an area second moment by rho t to come up with the mass moment. Then we remove the expression for the mass in order for us to write the actual moment of inertia in terms of a mass in kgs. Then we extended this to the parallel axis theorem. We said it's the same as the one for areas. Then we used integration to find the mass moments. And the last one was composite bodies. So in this topic, what you now can do is to actually calculate your moment of inertia in kgs square meters. Right, so that sums up our study for lecture number 8. We will discuss our last lecture, lecture 9, tomorrow. I wish you the best in these studies, and I think we have taken quite a long stride to do all our work in a very short time, but I believe that you're hard workers and you've got some good background. You came up with good grades and you came up to a very good program in mechatronics. I think you will and can make it. Right, so let's keep up the pace. Let's keep up the hard work and see each other in our last lecture. Have a good day. Thank you very much.